As we begin our Unit 2 of our calculus here, you're going to need to download the second packet. The first section in Unit 2 is Section 3.5, which is where we're going to start. What you're going to find is the rest of Chapter 3 is going to continue where the earlier parts left off. It's going to be tackling special types of trig functions and their derivatives, like in this section, derivatives of trig functions. And it's going to be covering more special rules that you use in certain scenarios. So as I stated, right off the bat here, we need to be able to cover the derivatives of all the trig functions. Okay, so let's start with a derivation of the derivative of sine x. That's our first stop. So in order to do this, we need to define two limits. The first limit we're going to define is of the function sine theta over theta. The limit as theta goes to 0 of this function is always going to be 1. The second function we have to define is, for its limit, is the cosine theta minus 1 over theta. The limit of x or theta approaches 0 of this function is going to be 0. Now, it is kind of, I'm not going to just leave it as take my word for it. We're going to prove these functions' limits analytically later, but for now, we don't have the tools to do so. So what I did instead was I'm going to show you on the graph what these limits are. Now note, both of these, I'm going to replace theta with x in the graph, but both of these limits are approaching 0. So let's take a look at a snip of Desmos right here. So if you can see, the red graph over on the left over here is y equals sine x over x, which is our first function. What we need to do is we need to find what the behavior is as x approaches 0. It appears that both sides is approaching a height of 1. Therefore, the limit in this scenario is going to be 1. Okay, so that's our first one. What about our second function? So we have this guy here, y equals cosine x minus 1 over x. Again, what we need to do is we need to approach it from both sides. It appears that both sides are approaching a height of 0. So if we go back to our notes, we can clearly see that we have a limit of 0. So all I want to do is visually show you that these are very easy limits to see. It just so happens that calculating them analytically, we actually, believe it or not, don't have the tools for that yet, because there is one more limit section coming in the middle of chapter 4. Okay, now that we have these two definitions, it allows us to actually prove what the derivative of sine is. So if you recall, this is our formula for the derivative of any function. This is the large formula, not the shortcut one. We have to use the large formula for this. So what does that look like? So in this scenario, it would be the limit as h goes to 0. We have to do f of x plus h, so we have to put x plus h in there. So the sine of x plus h minus the original function sine x all over h. Okay, so we start there. That's our first step. It says, recall from pre-calculus that the sign of the sum is defined as follows. Okay, so here we have basically a nice little shortcut definition that you learned in pre-calculus of the sign of the sum, which is sine, cosine, cosine, sine. So we can actually now take this guy and expand it. So that's what we're going to do. So limit of h goes to 0, we're going to get the sine of our first variable, the cosine of our second variable, plus the cosine of our first variable times the sine of our second variable, minus, so by the way, this is all one quantity where the green is, minus sine x over h. Now, there's no way to simplify this. There's no like terms, but what I'm going to do for the purposes of our proof is I'm going to move some things around. So I'm going to take this, I'm going to leave the first term where it is, but I'm going to move the sine x into the middle, since right now, even though I separated these with brackets, they don't really have a purpose in terms of mathematically what we're doing here. So I'm just going to switch these two terms, keeping their signs, just like this. Okay, so here, if you look closely at the result, we can break apart the entire limit into the sum of two limits, each of which will reveal one of the limits defined at the top of the page. Now just evaluate to determine the derivative of the sign. Okay, so that's what we're going to do. We're going to split this into two pieces. So first, the limit of h goes to 0 of sine x cosine h minus sine over h plus the limit as h goes to 0 of just cosine x sine h over h. Okay, so we are allowed to do this because technically you can separate this into two pieces just like any other fraction. So you could take this piece and then you can take this piece together, and that is perfectly fine to do. There's no issue with doing so. And we can also split it up by limits because you learn that the sum of a limit is the limit of the sum. So this is a legal situation, or in terms of mathematics. Well, if you look closely at the first function, we actually have a greatest common factor in the numerator. Okay, so we currently have this. All right, so if you look closely at this, look at this right here. So we have sine theta over theta. If you look closely, we actually have that right here. If you look at this, we actually have that right here, which means in this context, we can actually remove the sign. So remember, this is all multiplication and division, right? So that means we can actually separate the sign out, and we can do basically the following. Now note, this is a big deal that students sometimes don't understand. So look at the variable that we're dealing with the limit. The limit variable is actually h, which means any other value has no bearing on that limit whatsoever and can be treated as a constant value. So basically, what does this look like? It's going to be the sine of x times the limit as h goes to 0 of cosine h minus 1 over h plus the cosine of x, which we can bring to the outside, times the limit as h goes to 0 of sine h over h. Okay, so if you look at this really closely, the quantities that I was talking about are right here and here. According to our rule book here, the limit is sine theta over theta as theta goes to 0 is 1. So that means this entire orange quantity here is 1. And according to our theorem up here, the limit of this function on the right side is equal to 0. So this is 0. So if we write this out, we're going to get sine x times 0 plus cosine x times 1. And if we simplify everything, we get just cosine x, which means the derivative of sine, believe it or not, is cosine. Okay, so we can, if you look at the bottom here, I did a nice little summary for you. So we already proved this. It turns out that if we do this the same exact process, like if we did derivative of cosine, limit of h goes to 0 of cosine x plus h minus cosine x over h, and we went through all of this process again and again, we will end up with the derivative of cosine being negative sine. So those are going to be our first two important definitions for the derivative of trig functions. So interestingly enough, we can actually use those definitions in order to prove some of the other trig function derivatives. So if you move on to the next page, what we're looking at we need to find the derivative of tangent x. Now, we don't know anything about tangent x directly, but we do know what tangent x is equal to in terms of a trig identity. So if you go back to your old trig identity sheets that you have from long ago, you would know that the derivative or tangent is equal to sine over cosine. So what do we have right now? We have the derivative of a what? Okay, hint, hint, previous section. We have a fraction, so we have the derivative of a quotient, which means we can use the quotient rule in order to derive this specific derivative. So what does that look like? So remember, the top is f and the bottom is g. So what are we actually doing? So we're taking the derivative of f to start. We're multiplying by our original g. Remember, we subtract. Then we take our original f, sine x, and we multiply by the derivative of g. All over our g quantity squared. Okay, so what does that look like? Well, we don't have to do a lot of side work here. I think we can just write it all out. So the derivative of sine, well, look what we just learned. The derivative of sine is cosine. Okay, bring down the other cosine. Bring down the sine. And what is the derivative of cosine? Well, right here, it's negative sine. Okay, so basically, I'm going to put parentheses just so they're all separated, but that's your quantity. Now note, in trig, if you square a quantity like cosine, like this, that's equal to cosine squared x. It's not equal to cosine x squared. I know that's kind of weird, but these two are the same, and these two are not the same as the one below. So we would write this as cosine squared x. Okay, if we keep on going, we're going to get cosine squared x here. The negatives, which are here and here, become positive. We get sine squared x, positive, over cosine squared. Okay, take note here. If you want to make me convulse, then what you're going to do is you're going to try to cancel these out, right? Please do not do that. You can never do that. It's the same as saying something like this, right? So we clearly know that this is equal to 5/2. But if I went like this, what would be my answer? It would be just 3, which is absolutely wrong. So you cannot cancel those out. It's illegal. Instead, we want to use our identities again. Look at the numerator. What is cosine squared plus sine squared? Or in other words, what's sine squared plus cosine squared? It is equal to 1. So we get 1 over cosine squared. Well, 1 over cosine is the same as secant. So that means that the derivative of tangent, believe it or not, is secant squared. Okay, let's derive another one. We'll summarize all of these in a second. So the derivative of secant, well, again, we don't know anything about secant directly, but we do know its relationship to cosine. We just talked about it right here. It's 1 over cosine. So if you look at this closely, we again have a quotient, which means we can go ahead and use the quotient rule in order to derive this function. So how do we do that? Well, remember that the top is f, the bottom is g. So we're going to do the derivative of 1 times our original function cosine minus 1 times the derivative of cosine itself. All over cosine x quantity squared. All right, so lucky enough here, we have the derivative of 1 is 0. So we're going to get 0 times cosine, and then minus the derivative of 1 times the derivative of cosine, which is negative sine. All over cosine squared x. Okay, moving over here. So this whole thing here becomes 0, and the two positives cancel each other out. So we get a very bizarre answer of sine over cosine squared. So just FYI, technically this is the derivative of secant. But we actually, in all books and all things that we talk about in calculus in terms of derivatives, we don't actually express it that way. So how do we express it? Well, We separate it into pieces. So first we get 1 over cosine times sine over cosine. Okay, so if you look at this in detail, just some students have a very difficult time seeing this to this, but if you reverse the process and go the other way, they can clearly see that this down here is equal to what's up there. So just realize they're the same thing. So if we derive this, 1 over cosine is secant x, sine over cosine is tangent x. So the more common definition of the derivative of secant is secant tangent. So again, these functions, the functions we haven't derived are, we got, where are we? We got cotangent, right? We didn't do yet. And we got cosecant, which we didn't do yet. Well, the proofs are almost identical. Instead of sine over cosine, this would have been cosine over sine. We do the same process and we get a different result, which I'll show you in a second. For cosecant, we would do, instead of 1 over cosine, we would do 1 over sine, do the same exact process, get a little bit different result. So what are those results? They are right here. And again, this is your next big box of derivatives to memorize. Again, if you keep on having to go back to your notes to look at these, you're at a disadvantage. If you're moving on to calculus 2 and 3, you're at a really big disadvantage if you don't memorize these immediately. So, if you look at these derivatives, some students get a little overwhelmed because they're like, oh, I have to memorize this. But there is a little bit of a shortcut. So, I claim that you only really have to know these guys on the left side. Why? Because if you match these by their cofunction, so sine and its cofunction cosine, tangent and its cofunction cotangent, secant and its cofunction cosecant. If you memorize how they match, it's kind of a pattern that develops. So for instance, the derivative of sine is, of course, cosine, right? So we're looking right here. But if you go to the cofunction of sine and go to cosine, the derivative of it is going to be its cofunction, sine, but with a negative in front of it. Now again, what if you go to tangent? The derivative is secant squared. Well, if you go to the cofunction of tangent, which is cotangent, right? The derivative of that is going to be the cofunction of this, again squared, but with a negative sign in front of it. So there's a really big pattern here. So last thing, if we have secant right here, the derivative is secant tangent. But if we take the derivative of its cofunction, cosecant, then the derivative is the cofunction of secant, the cofunction of tangent, with a negative sign in front of it. So there is definitely a pattern that you can develop here. Some students just memorize them all, which is cool, and probably better, but there is a little bit of a helper here for students that have trouble with memorization. But you need to know these functions. You will be asked for these all the time. So be ready for being able to use them, and that's what we're going to do right now, is do some examples. Okay, if we went back to our first section on rules of differentiation, we learned the rules pretty slowly. So we didn't know anything about all the different concepts involved with derivatives, so we had to really go through the basics. Now, realize that essentially this is the basics. So I'm not going to be like, hey, what's the derivative of cosecant, and that's it. Like, that's not it. So now that we know all the rules before this, all the example problems are going to be using things that you've learned before. So are you going to be able to apply trig derivatives to all the previous material, including power rule, including product quotient rule, all of that. So you have to be ready for anything when it comes to this. These sections that you come up here are not going to be separated from the previous sections. They're going to build on the previous section. So number 1, it says y is equal to secant x minus 10 tangent x. Our goal is to find the derivative. So we need to find dy dx for this problem. Okay, so remember, if you have a minus sign or a plus sign between two functions, the derivative of a difference, so this is the same as the derivative of a difference, is the same as the difference of the individual derivatives, right? Okay, this is something that you've already learned before, but I want to be clear that it doesn't change when trig is involved. Now, are you going to write out either one of these two steps? Maybe not. You might jump right into the problem, and I am fine with that by just finding the derivatives. For example, the derivative of secant is right here. It is secant x tangent x. All right. Well, what's the derivative of 10 tangent x? Well, note, there is technically a product going on here, but as I gave you as a hint in the previous section, if one of those products is a constant, then you're kind of wasting your time with the product rule. Instead, you want to treat it as a constant times a function. Therefore, what do? You take the constant, comes along for the ride, and you take the derivative of tangent. The derivative of tangent is right here. It is secant squared, which means the derivative of this function is simply just secant tangent minus 10 secant squared x. Okay, number 2. Y equals e to the 2x cosine x. So hopefully by this point, after you have taken an exam on this, after you've done a ton of homework and labs, that when you see this problem, literally product rule is screaming at you in your brain. Why? Because we have a function with x on the left side and we have a function with x on the right, and clearly there is multiplication between them. Neither of them is a constant, which means this is a perfect example of the product rule, which means, again, we're doing f prime g plus fg prime. So we want to make sure we can go through this and get this exactly. So dy dx, let's just jump right into it. What is it going to be? It's going to be the derivative of our first function, e to the 2x, times our second function, cosine x, plus our original function, e to the 2x, times the derivative of cosine x. Okay, if you want to do a little bit of shortcut work here before we put it all together, feel free. For example, the derivative of e to the 2x, again, you should be very familiar with this. This is simply going to be 2e to the 2x. And the derivative of cosine x you just learned, that is negative sine x. So we can throw that here. So now in the next step, we can do all the simplifying at once. So it looks like the order of this is not of supreme importance, but I'll show you a little bit of shortcuts. So 2e to the 2x cosine x would be our first term. Note, this negative sign is going to change this to a negative. So we're going to get e to the 2x sine x here. And just so you know, again, an alternate result. Sometimes in the textbook, when it comes to e's, what they'll do is they'll factor out the e to the 2x and get 2 cosine minus sine inside the parentheses. So again, I am not going to be picky with that, but if it does come up, let's say in my math lab or something like that, just be aware that that might actually be happening. Okay, so again, we move to number 3, and once again, the light bulb should be shining in your head, screaming at you saying quotient rule. So once you see that, you can go, all right, well, let's see how this all comes together. So dy dx, we got here, remember our product rule is this, so our quotient is f prime g minus fg prime over g squared. So that's going to look like the following. So the derivative of sine x times our 1 minus cosine x. Remember subtraction for the quotient rule. Then we rewrite our f and then the derivative of 1 minus cosine. And this will be all over our denominator squared. Okay, we can do a little bit of shortcut work here. So the derivative of sine x is cosine x. The derivative of 1 minus cosine. So be a little careful here. So the derivative of 1 is 0 minus, what's the derivative of cosine? So cosine derivative is negative sine x. So if we do that, we're going to get 0 minus a negative sign, which is positive sign. All right. So if we write this out, what does that look like? It's going to be cosine times 1 minus cosine minus sine times sine all over 1 minus cosine x squared. So you could have combined these if you wanted to into sine squared. You could also distribute and do all the fancy math. Matter of fact, this might even come out to something even more fancy, but in terms of simplifying. But as I stated earlier on, after you do the quotient rule, you basically can finish your result right there in terms of your problem. I forgot to box this before. So you can finish your result right there, and I'm perfectly fine with that. It's showing me you know the quotient rule, and everything is all good. Okay, so what about this value? Y equals negative cosecant x cotangent x. Now, you might not know this yet, but believe it or not, that is actually by itself, let me just get eraser, that is actually by itself the derivative of cosecant, which means if I'm asking for the derivative of this, aren't I asking for the second derivative of cosecant? Yeah, the answer is yes. So I mentioned that here. So believe it or not, I am finding the second derivative of cosecant by doing this. So let's go ahead and do that. So hopefully, again, what's staring at you, you have two functions, f and g, let's say, and there's a product here. So we have to use the product rule. Even though we don't need to do this, I'm going to separate them so that we're using the negative in for f when we go through the process. So dy dx is going to be equal to the derivative of negative cosecant x. 1 second. X times our original cotangent x plus negative cosecant x times the derivative of cotangent x. Alrighty, so a little bit of, we can do a little shortcut work here. So what's the derivative of cosecant? Alright, so derivative of cosecant is right here. It's going to be negative cosecant cotangent. Well, we want, so what I'm going to do here, just because I want to be clear with this, is that the derivative of this itself is going to be negative, and then the derivative of cosecant is negative cosecant, I keep doing that, cosecant x cotangent x. So what are we going to get? We're going to get positive cosecant x cotangent x. Okay, what about this guy? Well, what's the derivative of cotangent? Well, we go over to cotangent. Derivative is negative cosecant squared. Okay, so all we have to do is basically collect things together. So if you look at this closely, we have cotangent times this. So that's going to be cosecant squared x, cotangent x. We have this times this. So the negatives become a positive, and we get cosecant cubed x, which means this is the derivative of this, and also the second derivative of just cosecant. Okay, so the last problem is much needed at this point. Much needed. So it's been a couple lessons since we did a problem like this, but I want to make sure that you understand that all of this is still in account. So this question is asking for the slope of the line tangent to the graph y equals x sine x at x equals pi over 3. Okay, so we've talked about this before. This is an incredibly important topic. A couple sections ago, we talked a lot about the equation of the line tangent. This is only asking for the slope, so we don't have to do y minus y1 equals x times x minus x1. We just have to find the slope only. So how do you do that? Well, you should know that in order to find the slope of a tangent line at any point, not just x equals pi over 3, but at any point, is just to find the derivative of the function. So right now we have this function. So what are we looking at? Again, light bulbs should be flying in your head, lit up in your head. This is two functions. It is an f, which is x, and a g, which is sine x. So we need, again, the product rule. So what does that look like? It's going to be the derivative of x times our original function sine plus x times the derivative of sine. All right, so quickly, we know that this is 1. We know that this is cosine. So our resulting derivative is going to be sine x plus x cosine x. Okay, so this is our derivative. Okay, so basically this is our first step that we need here. So remember, this is the slope of tangent at any point. Okay, luckily in this problem, and by the way, this is what you would give them if that's what they asked for. But in this problem, they specifically are looking for the slope of the tangent at x equals pi over 3. So what we need to do basically is find what the slope is. So the slope is going to be equal to taking pi over 3 and subbing it in to our function for x. Okay, hopefully you can see why I'm doing this with you, because a lot of students will lose their minds once trig is implanted into calculus. Why? Because not everybody came from my class, ha ha ha, joke, and knows trig. But if you came from a different professor, or maybe there's a ton of variables at play here, whatever it is, you might not know trig very well. Well, you got to know it for this class, so that's why I'm doing this example with you, because I want to bring out all the important things going on here. So first things first, pi over 3 is in the first quadrant, right? So if you do all students take calculus, we know in the first quadrant all trig evaluations are positive, which means that when we do our trig evaluation of this and this, the result is going to be a positive ratio. That's the first thing. The second thing is we need the actual coordinate for all pi over 3 angles. What is that coordinate? It is 1/2 root 3 over 2. Okay, what else do we have to know? Well, the sine of any angle, let's say theta, is always going to be equal to the y-coordinate. The cosine of angle theta is the x-coordinate. Also recall the tangent, which we won't need here, is y over x. So what does that mean? So if we're looking at this problem, if we want to find the sine of pi over 3, the sine is the y-coordinate of our pi over 3 angle, which is a positive root 3 over 2. Okay, let's just do shortcut work here. The cosine is going to be the x-coordinate and be positive, so that is 1/2. So if we do the math here, we're going to get root 3 over 2 plus pi over 3 times 1/2. Well, pi over 3 times 1/2 is root 3 over 2 plus pi over 6. Now, just a note here. Some students will immediately launch into decimal work right here. Do not do that. That is a horribly bad habit. If this was an application problem, like a word problem, and we need to find measurements and such, then yeah, we would launch into decimal work, because we need that in order to do measurements. But in any other scenario, if you're finding trig evaluations, I want the exact answer, which is going to be all fractions and pies and radicals, all the wonderful goodness of trig. I do not want to see the approximate answer, which is the decimal. So this is what I'd be looking for the slope of the line tangent to that function at pi over 3.